Um, yeah, so like Hope said, I'm a professor at U Chicago, in Chicago, and I lead a research group there. And obviously, we don't build products, so I'm not going to say anything about experience building any products. But I do want to talk about a problem that I think you may be facing in coming months if you haven't yet. Okay, and this is a problem we have been working for at least a year now, and I've been evangelizing this problem and the solutions for the next since last year, and I'm seeing people more and more getting familiar with this problem now. So I'm very excited to share this with you. Right. So to understand why I'm saying this here, I want to briefly step back and talk about the research background, the landscape of internet application, the internet age for the last 3 decades. Okay, so if you think back from the early 90s all the way to today, the internet technology has been evolving for decades, basically be driven by application innovations. Okay, so you have web, you have search engine, you have internet video streaming, you have big data. They all contribute to new paradigms in systems research and how you think about computer systems. And today we have generative AI, and it is already gaining enough popularity to change the way people think about system research. And what we want to ask, the question we want to ask is, what might be the architecture for generative AI? Okay, now, I want to use internet video streaming as a use case to tell you where I think we are in this timeline. Okay. Now, the reason I use internet video is I've been working on internet videos and multimedia systems for actually for almost 20 years now, since my PhD years. And if you look back, people spent about just a few years to figure out how to build video websites and how to build video players. And then it took us almost 20 or 30 years to figure out how to build a global distributed systems to make internet video work well for the whole human race, right? Now, if you think about generative AI, especially large language models these days, people just started working on how to build applications and how to build one single server to speed up one single request, right? So that's where we are today. And I believe there's still going to be a long way for us to figure out what is the best way to build internet, global distributed systems for these large language model applications. Okay, and so basically, I believe we are still very early stage in building the systems for this in this large language model ecosystem, and there's a lot of work to do. And one thing in particular I want to talk about today is this idea called knowledge sharing. Okay, how to share knowledge efficiently across large language models. Now, why do I think large language models need to share knowledge? Now, first of all, you may think large language models are already good enough because they're trained on the whole corpus of internet data. But think about this: the internet data is not so powerful. It's not powerful enough for all models to know the newest data, right? Personalized data, and maybe internal documents that you don't want the OpenAI models to know. So there are a lot of ways for models to be paired with domain-specific data. And the way, this basically is a new paradigm of serving large language models, so-called in-context learning. Probably a lot of you with ML background would know what I'm talking about. Basically, when user launch a query, the query doesn't probably the language model itself didn't know how to answer that query, but the language model knows where to get information. Now, the retrieval of that information is a separate problem, but once you know which document will be relevant to answer that question, the model can read the documents on the fly and give you a good answer. So that's basically the in-context learning problem. And if you think about this, there are a lot of use cases. Like you can let the model read a book that's maybe a new book the model didn't know before, and maybe it want to launch queries about news today, or maybe business documents, internal business document of a company, or maybe just a chat or shopping history of a user. These are all information that you want the model to know on the fly for that particular query. But think about what the implication of the system side. The implication is the model now needs to read a lot of data in real time. Okay, how to build a system for that? Okay, that's basically the problem we're trying to solve. And the system problem here is if you have tried to let the model read a document and answer your query, you probably will realize the problem like this. Every time you ask a model to read a book, for example, it has to do prefill. It has to learn. The technical term for that is so-called prefill phase, if you know the literature. The problem is the prefill phase takes a while. every time you ask the model to read a book, okay, it takes a while for the model to prefill and build a so-called internal knowledge of the internal understanding of that document called KV cache, okay? And the KV cache, I mean, the delay of prefilling a document, it's only get longer and longer because the model have, that's the selling point of latest models, right? These models have bigger, longer context window. The models are capable of reading longer and longer text, but at the same time, the delay to read this text is going to be longer and longer. And also, users will get less patient. Okay, they don't mean like people probably can tolerate 5 seconds delay today, but maybe in the future they want really interactivity. Okay, so what we want to, the vision we're investigating is this so-called thing called knowledge sharing. So let's say if you have a model read one document, well, so it takes a while for the model to learn the information of that document, but the KV cache, this yellow box, can be shared across models. Okay, and that sharing is the critical ingredient here, because when the next time you have a query about that document, the model can immediately respond using the KV cache shared from the first model. Okay, and that sharing is the key here, because basically every time you have a new information, you just need the model to learn it once. Now, of course, this learning is not fine-tuning, you're not fine-tuning the model, you're not changing the model, but you can let the model process the information into a representation called KV cache that the model is a different model, a different instance of the same model can readily use to answer questions in the future. Okay, so that drastically speed up the things. So here is the demo. My student made this demo. On the left, you have this context document, which is the background context you want the model to read. And on the right, you have two instances of LLM models serving on A for the GPU. And you can see here, so what I'm trying to say here is there are two queries sent to this document, sent to these two GPUs, and the two GPUs running the same model will give answers. The first time so it's playing now. So the first time you launch a query, the model takes a while to build that KV cache. Okay, it takes a while to build a KV cache, so that the delay of the first query will be pretty long, right? About 60.5 seconds. But the second time you have the query coming in, the KV cache can be shared. Okay, now this kind of makes things much faster. In this case, 7x faster. I hide something here because the sharing of KV cache is not going to be that straightforward. I'm going to talk about that in a second. But once you have a way to share the KV cache efficiently, things can move much, much faster. So going back to this vision, it's not going to be just making things faster. It's also making the throughput higher, because the prefill phase takes a lot of resource, not just kernels, but also GPU memory. Now, this is all kind of very promising, but you may wonder, first of all, why there are knowledge that can be shared across different users, right? One reason is this 20-80 rule, right? So this is actually well known that 20% of your knowledge will be used 80% of the time. We hypothesize that 20% of the context will be used by 80% of the of the language model queries. And second of all, if you know a little bit of background, you will notice KV cache is pretty big, right? But the good thing is KV cache, storing KV cache on device, on say SSD, is actually much cheaper than recomputing the KV cache every time on GPUs. Okay, and this gap gonna be even get bigger, because longer context or bigger models, the KV cache size is growing actually slower than the prefill delay, the computation to create this KV cache. So caching these KV caches is actually a good idea. Now, about a system architecture, I'm not going to talk too much about the details, I guess. But the system architecture would look like something like this. At a very high level, you have a storage layer to the right. You have something in the middle to share the KV cache across different instances of language models. And finally, you need a layer to combine the KV cache learned by different models, so that in the future, the model doesn't need to learn the information again. Right. So I'm going to briefly talk about these three layers, the challenges here. First of all, the knowledge caching thing, I think this is actually a good use case for solutions like Alluxio. Basically, this is a object store with pretty big objects. But if you think about the knowledge retrieval part, like I said, KV cache is pretty big in size. So if we want to share KV cache from one GPU to another, the transfer of KV cache might take a while. Even though it's pretty cheap to store them, sending them over the network can be quite slow, okay? So the first contributions, the technical contributions we're making here is try to have a encoder of the KV cache such that the loading can be much faster, okay? And second, and finally, you need some way to synthesize information pre-filled by different model instances. So what I mean by that is sometimes when the model learns, will need information from different documents. Okay, well, I want to ask you questions about the information of this user, but maybe the information about this user is in 2 different documents, and these two different documents may be prefilled separately. So you want to combine the KV cache of these 2 documents together in order to answer the latest question. So how to do that? Well, you need a system to synthesize the KV cache when a query that requires multiple documents come in. Okay, so I actually don't know how much time I have, and I'm not tracking time, but I hope I can spend some time to talk about the first technique. It will be impossible to talk to both things because it's going to become a conference research talk. So I'm going to just briefly talk about the first thing, about how to compress KV cache, also called encode the KV cache into a much smaller size so that the loading of KV cache becomes much faster in the future. Okay. So the idea, so this is basically a research paper we will be presenting at a networking conference this summer, and you can find the archive paper online. So let me just briefly recap the problem again. So if you have a KV cache, which is pretty big in size, you want to load the KV cache, which is the red bar here. The loading of KV cache without compressing, the loading of KV cache will take a while, so the whole delay is not going to be reduced much. But if you can compress the KV cache into a much smaller size, loading the smaller size KV cache is going to be much faster, and the overall delay can be much lower. Okay, so this is all you want. You want the faster prefill, even if the KV cache is not stored locally. Now, how to do that? This is just a high-level overview of the technique. Again, this is just a more detailed view of KV cache. You have K tensor, V tensors, and you encode it into binary representation. And the binary representation will be stored in somewhere S3 or local SSD or some other servers. And then when the query about the same KV caches, the KV cache can be reused for a new query again. The binary representation will be read back into GPU, and the GPU can decompress it into something readily usable in GPU memory. I want to stress that this is basically transferring this KV cache tensor into binary representation. This is not just reducing the memory usage of KV cache in GPU memory. This is trying to encode it into a much more compact binary representation so that you can store it and transfer it more efficiently. Okay, this is complementary to recent techniques like quantizing KV cache. You probably have heard this work, quantizing KV cache, or dropping a few tokens from the context, or maybe just dropping some columns in KV cache directly. They're orthogonal to us. They're basically saying they all keep the KV cache tensor size, but what we want to do is to translate KV cache into binary representation so you can store them and transfer them efficiently. Okay, now here's the question. Why do I think KV cache can be compressed? And why do I think KV cache can be compressed efficiently? Now, this is a little bit background of my own research journey. I've been working on video compressing and video compression and video streaming for almost like more than a decade now. And I can see from firsthand that KV cache is basically 3D tensors, and 3D tensors can be compressed in all sorts of ways. Video compression has 20 years of research literature, and there are a lot of ideas we can borrow there. Okay, so the idea is there are actually a lot of useful distributional properties of KV caches. For example, if you really open up the box of these KV cache models and you can visualize the values of these KV cache values, okay, you can see there are actually locality, there are smoothness between neighboring values. Okay, so that's one opportunity. The other opportunity is you want to do quantization, but different values in your KV cache, different positions in your KV cache have different sensitivities to quantization. You can quantize certain part very aggressively without affecting the quality of the service. Finally, this is the opportunity to binarize a KV cache. Basically, once you quantize the KV cache, it becomes very easy to entropy code it, and the entropy coded representation will be much more compact. Okay, so I'm gonna move faster here. Just want to show you this visualization that the KV cache values are actually having some locality. Look at on the right. The values are not totally random. There are values that look similar, at least horizontally. Okay. And okay, so I'm gonna just quickly show these slides because I guess I'm over time now. But this is a graph to show where early layers of so shallow layers of a KV cache, basically values that are produced by shallow layers of large language models are more sensitive to quantization than later layers. Intuitively, because early layers, errors on early layers will propagate through different layers. Okay. And finally, you can, this is architecture. You have a KV cache, you compute the delta because the values similar, neighboring values are similar, and you quantize it. And finally, you do so something called adaptive arithmetic coding, then make it a binary representation that's more amenable to disk storage and network transfer. Okay, I'm gonna just try to move a bit faster here. Okay, just to give you the impression what the result would look like. Okay, so we pick an example here, which is a data set, a very common data set called LongChat, and the model is Llama 2 7 billion model, and the network link between them is 3 gigabit per second, which is typical to cloud server bandwidth. And here's the result. So on the left, you can think about this is a compression efficiency. X-axis being the KV cache size, Y-axis being the quality. Accuracy is the quality metric here. And top left is better. And you can see what CacheGen does is, well, it can achieve same quality with much fewer with much fewer bits, basically. Okay, and because you can represent KV cache with much fewer bits, on the right, the time to generate the first token can be much shorter. Okay, because the KV cache can be transferred from storage to GPU memory much more And on the right point, this gray right point to the right is basically if you don't have KV cache, you're going to wait for more than 6 seconds for the results to come back. Okay. Okay. This is a breakdown. I'm not going to bother you with that. So, okay. So we have a research paper, of course, but also have open source projects. So feel free to check it out. I do want to finish the talk with this graph, which is what we envision how the world will see this knowledge sharing system and how the world will view whether a knowledge sharing system is good or bad. Okay, so basically there are 2 key metrics. There's a cost, which is storage cost, compute cost, and so forth, and also the delay. Now, the naive way today, the default way is every time you do prefill again and again and again using GPU cycles. This is going to be very expensive, somewhat slow, and you can naively store KV cache at different places. For example, you can store it in CPU memory, which is more expensive in some way, and also SSD or S3. But you can see they exhibit this trade-off between cost and delay, right? You can spend more money to store KV cache, but and delay will be shorter, or you can use cheaper devices, but the delay will be much higher. So what we want to do, this line of project, is trying to make the knowledge sharing much more efficient. Okay, and I want to stop here and say, well, if you're interested as a potential user or contributor,